We're back with the next session and the next talk for the today. This talk is going to be about faster applications, harnessing Python with C, Zig libraries, and a story for Akhil on building the fastest LLM tokenizer. Well, yes, can we welcome Akhil on stage? He's the machine learning and a data engineer and also an open source contributor. So can we have a big round of applause for Akhil?
So hi guys, very good morning on Sunday. Thanks for being here. So let's start. So myself, I'm a senior data engineer in machine learning at one of the popular Singaporean banks. And my bread and butter is into Python. That's like what pays me. And Rust and Zig is my passion. As in of the work, I try to like contribute in this particular domains. And I also like have my own tech blogs. I write short stories. And if you guys are interested, you can just follow me on Twitter, which I regularly like post some tech tweets. Okay. So before even talking how to make our Python applications faster, let's see like what are the main reasons that make our applications slower when we program in Python. So there are like many couple of reasons. So one is, as you guys already know, that Python is an interpreter where in the execution it passes the code line by line, translates it into a bytecode, and then executes on the VM, which takes kind of a large amount of time compared to compile languages, where you compile it once and run it on the machine. And then we have a garbage collection, which is again kind of an overhead. And then there is a type check that Python performs before it executes. Like for example, let's say if you're adding an integer with a string, so it type checks what are the types that is being executed. So before even performing that operation, if the types are incompatible, it errors out. And then in multi, if you are trying to execute your program in a multi-threaded environment, like spinning up multiple threads, because of gel, at any time only like one thread will be like active. So even if you spin up many multiple threads, but any time only like one thread will be like performing the execution. So these are like the kind of major bottlenecks that you see while running your applications and why they are like slower. So how you can actually solve it? So one way it is to like bypass the whole VM. That's by interfacing your applications with other languages which don't have like these overhead. So there are like couple of languages like C, C++, Rust, Zig, which will actually help you in bypassing the VM restrictions and make your applications faster. Then what are like the benefits? Like I have already iterated. So there's no VM. It's simply your machine code that directly runs on the CPUs. And there's no garbage collector, as in there's no overhead of doing automatic memory management. But the trade-off is that you would need to control like deallocating the memory and allocating the memory. So the overhead will be on the developer. But to make applications faster, you can avoid garbage collection. Yeah. So Python is like a cat. It's kind of a domesticated animal where you actually like to cuddle with. And the other language like C is kind of a cheetah. Like it gives you the speed and everything, but it's not. It cannot be domesticated, as in you can't like keep it at your home and cuddle with. So if we combine these two, and this is what we get. It's a wild cat. It's called Ocelot, and this Ocelot animal, it can be domesticated, but you need to like live in the forest. So, how you can actually integrate Python with C libraries? Like yesterday, we saw the talk from Goel, where his presentation was like from C context, how to build the Python modules and everything. But this talk presents you like from the Python point of view, how to actually declare C data types in Python and then like interface with C ABI compatible libraries. So in Python, there is a inbuilt module called C types, which offers you all the C data types and structures. So this whole sheet, there could be like 15 or like 16 data types. So these are like, you can see there are like two columns, C type and Python type. So this is kind of like a matching between the two. In C, like what are the data types that we have, and in Python, like what are the relevant data types. So let's see like how we can actually use C types from Python to integrate with C libraries by seeing few examples. So these are like the baby examples. So this is like the hello world for C type for using C types. So here what I'm trying to do is that in C I've just created a simple addition function which just adds two integers, and in add.py, which is a Python file, I'm just like calling this function. Uh, so this is like how we're gonna do. In add.c, you define that function, you compile it as a shade library, and in add.py, using C types, you load that library, and you define the schema. Schema as in the functional schema that you have like created in .c, which are nothing but the archetypes and the return type. If you see lib.add.archetypes, so we are like passing two int parameters, and the return is a int parameter. So that's what we are like trying to define. And directly I'm calling the function, and I'm just adding the two numbers, which is 10 and 5, and I'm directly printing the result. And in the below card, you can see what's the result, which is 15. So this is like simple introduction for you guys to see how C types work. Let's see like more complex use cases. This is string concatenation. Here what I'm trying to do is that I'm trying to like add two words, like combine the two words. So here the left side is the .c file, which has like some kind of computation that goes on. So I will tell you like simply what's happening. It's very easy to understand. In the concat function, if you see, I'm just like sending two parameters, which are nothing but pointers to the sequence of characters. There's nothing but a string. And then I'm calculating the length of these two strings. And then if you're like concatenating two strings, so you need to like allocate space that's equal to like length of one string plus length of other string. So that's what's happening in malloc. And then what I'm trying to do in the last couple of calls is that I'm trying to like replace the new allocated memory where uh, the first partial gets filled with the first string and the second one will get filled with the second string. And I'm like returning the pointer to the sequence of the characters. And in .c, I mean concat underscore .c .py, you can see I'm just like calling this particular like function, and I'm concatenating the two strings, and you can see hello world is getting printed. So this is from usability standpoint. Now let's try to like explore the performance side. So here it's a simple prime number generator that I have coded in C and Python, and left side is the prime dot c and right side is the prime dot pi. The algorithm is same, but let's see like the performance, like which is performing best. So I'm trying to compare by generating the first 50,000 primes and first 1 lakh primes. So if you see, the pure Python is very slow in terms of like computation. So if you compare like Python with Scilab is performing very fast. It's giving you on an average 22x speed compared to pure Python implementation. So this is like what if you like interface with C, you can get good performance. Now let's go get into the story of me building the tokenizer and interfacing it with Python. So before even like I start explaining about the technical details, let's try to understand what LLM tokenizer is. So here if you see, so how many of you are fans of KGF? Like, do you know when KGF 3 is gonna get released? I mean, are there like any plans by Prashant Neel to make KGF 3? You don't know, right? So let's say there's a model that has been like created in the internal production house of Humbala Films, and like somehow you got access to that model, and you want to like ask whether KGF 3 is being planned or not to the LLM. Now LLM doesn't accept the English text as it is, so there are like few processing steps that goes on, and then like LLM will respond. Now what are the processing steps? The first thing is about tokenization. That's like where your English text or like any text is converted into token IDs, and the token IDs again each token ID will be mapped to some embedding vector, and these embedding vectors are like sent to the model. So the topic here is just to understand how the token IDs are like generated using a tokenizer. So this is like a small example. So here I'm asking, is KGF3 by Prashant Neel confirmed? And before sending it to the LLM, so the whole text is splitted into different token IDs. So if you see, is like one token ID, and space K is one token ID, GF is like one token ID, space 3 is one token ID, space by is like one token ID. So you can see the series of tokens that are like generated by the tokenizer. Okay. Now let's like dig into like how this tokenizer works internally. So for example, let's say you have a like large corpus of text. Here for this example, let's consider uh, the whole corpus of text contains these words: hug, pug, pun, bun, hugs. And if you calculate the number of words that are like present in the whole corpus, like for hug it's 10, pug is 5, pun is 12, and these are like the number of words that are present. Now initially we will create a set of characters, unique characters. So if you see V, which is nothing but the vocabulary, so H, G, B, so these are like the unique words that are like present in the whole corpus. Now, again, what we will do, we will like pair two characters and then again like count how many number of pair of characters are present in that whole corpus. So if you see, UG is like one pair of character, PU is like one pair of character, and when I like sort it in descending order, so UG is coming to be the maximum number of occurrences. So now I will like pair UG and then like add it to my vocabulary. So if you see on the top, so after like adding all the unique characters, now UG becomes my second addition to the vocabulary. Now I will try to like repeat the same process where UG will be considered as like one word, and then with UG I will pair it up with the other adjacent characters. So H, U, G, which occurs like for 10 times. P, U, G, which again occurs for 5 times. Then again in PUN, because you don't find UG, so again those will be like unique characters which are like appearing for 12. Now again I will like reiterate the same process. Now finally this is like my vocabulary set that I get based on the maximum frequency count on each iteration. So first are the unique characters, then pair of characters, then finally, so this gets like added up with respect to the adjacent characters that you have. And this can like go long, but uh, generally in tokenizers, whenever like you generate this pairing of different characters, you will put a hard limit. Like for example, in GP2 tokenizer, I think the hard limit is around 50,000. As in, when you have like 50,000 elements in your vocabulary, then you will like stop it. And each element in that vocabulary will get one number, which starts from like 1. So B gets 1, G gets 2. So this is like what you see here. So E is 3957 is nothing but the ID. So yeah, this tokenizer that I have built, I built it in Zig. So I just wanted to like spend some time on Zig semantics, because Zig is kind of a new programming language that entered into the space, and it's getting like a lot of hype. Let's really see the syntax basically. So this is a small Zig code. Now what it's doing, it's just taking an array, and then it's trying to like see if there like any presence of like characters like space and comma. If it is there, then it will like not consider them, and then it will try to like only like pass set of characters which are nothing but like numbers. If you see like 1, 2, 3, 6, 7, 8, 9, comma and 99, I'm just like passing this string into like array of numbers. That's it. But the main point that I wanted to like bring out is that Zig is very explicit. So right from memory allocation. So if you see in initialization of array list, so here std.arraylist u32. So I'm defining the type, and then dot init, which is in the parameters I'm sending li as a argument. Now what is li? It's an allocator. So there are like bunch of different allocators, like general purpose allocator, C allocator, and then like what you see in malloc, right, in C. So there are like different variations of allocators where you can actually send these allocators into functions, and within the functions you can use these allocators to actually allocate memory in the heap. So it Zig gives you like fine control about like memory. And if you see the defer statement, so defer statement, so generally in C, let's say you have allocated using malloc, but you will be like freeing the memory only at the last line when the function like uh, exits, right? Execution of the function exits, and you try to like free that memory. But here in Zig, there's a statement called defer. So this is like LIFO structure, as in the list.dinit function will not get executed after initialization, but this will be like executed at the end of the function. But you can have like clear semantics by pairing the initialization and deinitialization sitting side by side. So you need not actually worry in keeping track of deallocation at the last of the function. But by using defer statement, you can pair up your initialization and deinitialization blocks. And finally, this is just a simple test block. Now, in the last line, I'm just like comparing with the generation of the numbers with the expected value. If it is true, then the test binary will like execute successfully. Okay. Now coming to LLM tokenizer, the signature as in, so when I have like coded in Zig, so I need to like expose the C, it has a C ABI, right? Because it needs to like communicate with Python. Now the signature will be in this format. So where there are like simple two functions. One is a token ranker function and the other is an encode function. So the token ranker function will accept the name of the tokenizer, which sets up or initializes the tokenizer internally in Zig, and then creates a object, and the return value of this particular function is simply pointed to that particular object. And then in encode function, I'm sending the text that is to be like encoded with its sorry, not with its length, but the token length, which will again be inputted by encode function, and then the pointer to the uh, token ranker object. Now again, like as we earlier saw in few of the examples, so I will like compile my tokenizer library as a shared library in Zig, and I'm like directly loading it in Python. So again, same like whatever the structure that you saw earlier with respect to the library signature. So these are like my library signatures that I'm defining in Python so that I can interact with the Zig tokenizer. So this is for the encode function and this is for the token ranker function. And this is like a simple single file which doesn't have like any logic of how the tokenizer library like which doesn't contain like any tokenizer logic because it's already present in Zig. So here you're just trying to like glue, this is just a glue code, right? So whatever the things that we had discussed like earlier about C types and everything, so these are like present in this particular file. And if you see from line number 21, this is like how you're gonna like call from Python, right? You're just defining the name of the tokenizer, giving the library path, and in line number 25, I'm asking it to like tokenize this whole statement, and in line number 28, you will get the token IDs. Now let's see the performance. So how many of you are Triple R fans? No one. Come on here, we got an Oscar for it. Okay. So I've actually experimented with three different files. One is the Natu Natu song lyrics, and the other is the Python code of conduct, and the last one is a very huge file, which is Oxford Dictionary. So on the right, third column, you can see the any human can understand what's the quantum of size we are dealing with. So the first two are like relatively fine, but the third one is kind of huge. Now, if you see, I'm comparing with the pure Python implementation with the Zig implementation that I've done. So the Zig implementation like is very fast, whereas the pure Python implementation is like kind of very slow. So this pure Python implementation, I took it from Hugging Face Transformers library and compared the tokenizers for both. And just like make a note of this. So the tokenizer, it requires a regex regular expression library because Zig ecosystem is not yet matured. So I have like interfaced the Zig with PCRE2 library, which is built using C. So here, but if you see in the Oxford Dictionary, there is no metric. Now, why there is no metric? Because the Zig wasn't actually generating any token IDs. I think it was like, it just hung up. It just kept idle. It's not, it's processing, but it's not generating any token IDs. Now, why is it happening? So I have profiled the code of Zig, and when I saw the PCRE2 library that I was like talking about, which is nothing but the regular expression. So it was like consuming around like 93.5% of my whole execution, which was like useless because my main encoding stuff is the meat part, but the regular expression is just a kind of a minimal part that needs to be used. So I was like exploring different regular expressions libraries, but in Ziggo's ecosystem, as I already told you, it's not yet matured. So I was exploring in different other languages. So I found there's like one particular library which was like giving good performance, which is in Rust. So which is called Fancy Regex. And if you see, it's only like 0.89% of my total execution time is being spent here. And let's see what happens if I use the Fancy Regex library in Zig. And by the way, how many of you know there's this Rust implementation of the tokenizer by OpenAI? Anyone know like what it's called? Okay, it's called tick token. So this comparison, like I thought it would be cool or like it would be fun if I actually compare with the Rust implementation, and I was like, I went like bonkers because the Zig implementation was like performing better than tick token library. I like rechecked the code like twice or thrice. Like I thought I would be like missing something, and again like I wrote a validation logic, like whatever the token IDs that are generated from these three different implementations, whether like they are correct or not. So even like after doing all these validations, the Zig implementation was like performing good. Like for Natusong and Python code of conduct, it was giving a good performance. But for Oxford Dictionary, if you see, the performance wasn't great. Like if you see linearly, it like from code of conduct, it's like 4x, like for pure Python implementation and also for Rust implementation. But for like Zig, it's not 4x. So yeah, I need to like still dig deeper, like why that's happening. So yeah, so Zig was like performing superb. Yeah, that's it for the talk. And you can just like scan the QR code. You can go to the GitHub repo where you can find the whole implementation. I think I have like 2 minutes of more time. I'll just like run some demo of this so that you can get that feel. So this GitHub repo just contains a simple Docker file that contains like all the implementations, and I'm just like running the Docker container which contains the implementation of all these three, and I'm comparing the performance using Hyperfine. So if you see the tick token is done, the Zig is done, but the pure Python implementation is taking like a lot of time against code of conduct text. Yeah, patience. Okay, anyone have any questions until this gets done?
Please come to the mic. Yeah, we don't have much time, so we might take only one question.
Hello. Yeah.
Yeah, thanks for the session. It was very good. I just want to know, tick token uses Rust and Zig uses C Python, right? Or C?
No, no.
No?
Zig is a complete different language.
Okay.
It's like how you treat Python and Rust. So Zig also like falls under the same, as in it's a language,
Okay.
and you can write Zig code and you can compile it and then run on your machines.
And in the initial stages of the lecture, you were talking about the comparison between C Python and or C types
Yes.
usage and Python normal, right? What
Yes.
about the comparison with the C language?
C types, it's just acts as an interface. As in using C types, you can't build your performant applications, but you need to like write your C programs, compile it as a shared libraries, and then use C types to interface with the C libraries, and then build your performant applications.
Okay, thank you.
Yeah.
One out of context thing. Have you explored this language called Mojo?
No, not yet.
Maybe you should try it once. It's good. Thank you.
Okay. So if you have any questions, I will be there for another like half an hour. So yeah, you can meet me anytime. Thank you.
Thank you so much, Akhil.